Hello and welcome to my presentation, which is on the highly debated impact of elevated pore fluid pressures on episodic tremor and slip at Cascadia subduction zone. I will also briefly be touching on the two other key end members of strain dissipation here, but primarily there will be discussion on fluids and ETS and how they are structurally related. The Cascadia subduction zone is a convergent plate boundary where the Explorer, Juan de Fuca, and Gorda plates are moving eastwards towards the North American plate. You can see in this figure the motion vectors of the plates and the general orientation of the subduction, with the North American plate sitting on the east and the Juan de Fuca, Gorda, and Explorer plate sitting to the west. The Juan de Fuca plate is currently subducting at a rate of around 4 centimeters per year, and this subduction zone complex is one of the most exciting areas of research right now, due to the fact that Cascadia is an archetypal example of the relatively recently discovered slow slip phenomena, and also due to the ability of this subduction zone to unleash a magnitude 9 or greater megathrust earthquake that could devastate areas in the US and Canada. Before I delve into the phenomena of slow slip on Cascadia subduction zone, I think it's important to contextualize what lies both up dip and down dip of the slow slip region. The modes of strain dissipation for Cascadia are shown here in this simplified schematic of the area. Up dip, there lies the locked zone, where strain will be released by brittle means and large magnitude earthquakes very occasionally. This area exhibits velocity weakening and unstable slip behavior. Far down dip in the blue region, we see that plate deformation is accommodated by ductile shearing. This is sometimes referred to as creeping, and it is accompanied by little to no seismic signals, as there will only ever be locking on small asperities. In between, in the seismic aseismic transitional region, is where slow slip, including ETS events, can occur. A more realistic schematic is shown here, with the recurrence intervals of these events also shown, along with the region there in the transitional zone, where high pore fluid pressures are thought to facilitate ETS events. Slow slip events with associated tremors that occur over months or less are known as ETS, thanks to Rogers et al. 2003. These are events that in a continuum model would lie both spatially and mechanically somewhere between the ductile shearing that occurs far down dip and the locked portion up dip, between 25 and 55 kilometers depth. The exact depth range is debated heavily in the literature. Because of this, ETS has been observed globally across a wide variety of depths. It is thought that this is a pressure-insensitive event. The temperature field is typically between 450 and 550 degrees, but if you change the rheology model that you're applying to the lithosphere to a weaker feldspar rheology or a larger proportion of quartz, this can vary. Comparatively, ETS events have lower stress drops than earthquakes, with stress dropping around 100 kilopascals compared to the 1 to 100 megapascals of a megathrust event. Tremors and slow slip are believed to have a strongly correlated spatiotemporal relationship, as you can see in this receiver diagram. However, there have been instances of slow slip with no detectable tremor, which could be a result of instruments not being sensitive enough to trace them. They are typically measured by GPS. ETS occurrence within the Cascadia subduction zone depends on frictional properties and stress conditions, which is where the role of fluids is widely hypothesized to come into play, particularly in the Cascadia setting. The portion of the complex that hosts ETS events lies between 25 and 55 kilometers depth, and seismic data has revealed a thick layer that has anomalously high P to S wave velocities, which indicates elevated pore pressures in the subducting crust, due to the fact that S waves struggle to penetrate through fluids. This is shown in this very complex diagram from Zhu et al., where there's a lot going on here from this study where they focus more on basin sediments, but the key takeaway is the effective stress, which we'll come on to in the next slide, increasing with some scatter as VP to VS ratio decreases. Elevated pore pressure is thought to be a key trigger for ETS because it will reduce effective normal stress. Effective normal stress is a key concept here, in which stress acting on a plane is defined by subtracting the pore fluid pressure in the rock from any normal stress component. The matrix showing this general stress state is shown here, with the shear stresses remaining constant. High pore fluid pressures reduce the effective stress acting on a surface, and when it is low enough at near lithostatic pore fluid pressures, slip can propagate relatively easily. ETS is essentially a stress-sensitive process. Moving on to more detailed structural themes, Audet et al. Proposed a mechanism for ETS generation that involves firstly the liberation of fluids from the dehydration reactions in the subducting crust. These fluids will then help to achieve a state of overpressure, which is pressures above the hydrostatic prediction, within the subducting crust, lowering the effective normal stress on the plate boundary. The pore fluid pressures will continue to rise until they reach a near lithostatic state, and at this point the effective stress will be so low that slip can be triggered as a result of very low dynamic stress changes. This system is still widely agreed on, as you can see from these two schematics, provide a graphical representation of this exact process from very recent papers by Gosselin et al. And Nakajima and Ukida up to 10 years later. Hydrofracturing also plays a crucial role in this cycle, allowing fluid escape, which lowers the pressure and terminates slip propagation. This is caused by dehydration and brittlement. Dehydration and brittlement is where hydrous minerals, often serpentinites, will dehydrate and induce an increased pore fluid pressure as the liberated fluids accumulate within a low permeability rock. This process is often associated with the triggering of unstable faulting and earthquakes because it will push the Mohr circle of a rock unit closer to the critical yield stress, as we can see in this final figure here from Seung-hee and Hosseini. Eventually, fracturing will occur, allowing pore fluid pressures to fall again and the termination of the slip event. The general mechanism which we have just described, initially proposed by Audet et al., is still widely agreed on. We have learned much more on the minutiae of how fluids impact ETS generation and termination at Cascadia in recent years. This particular model emphasizes the effect of strain localization and microfracturing in a dynamically evolving brittle ductile rheology, where both fracturing and creep are important. Slow slip events are presented as ductile processes, which are a result of transient strain localization, and the tremor signatures, which we can see, are as a result of high pore fluid pressures causing hydrofracturing of the rock itself. A crucial part of this model is dynamic interplay between microfracturing and sealing. Microfracturing causes an increase in the porosity and permeability of a rock, and this is used as a proxy for pore fluid pressure, exerting control over fluid flow. At the point of maximum microfracturing activity, there will be intense strain localization and formation of a shear zone around these microfractures until they are healed, along with increased fluid pumping within the rock. There is a positive feedback loop here as the increasing strain rate induces more efficient fluid pumping and further increase of pore fluid pressure, leading to more microfracturing. However, fluid consumption via fracture healing will begin to take place and eventually become dominant, causing the pore fluid pressures to fall again and drastically reduce the strain rate. The non-uniform displacement during these strain localization events is thought to occur on kilometer scales at Cascadia and correlate with ETS events. In this model, episodic large macrofracturing events as a result of overpressure is the source of non-volcanic tremors. Baer and Bergman also suggested that silica enrichment in fluid-rich environments could cause healing and allow pore fluid pressures to accumulate again in the inter-ETS period. Going back to strain localization, more research and modeling has been carried out that builds on some of the stuff we just saw from Bernardin and Guedan. This research by Beal et al. Provided a detailed rheological modeling of SSE, including ETS. Their model similarly uses a brittle ductile regime with strong class and a weaker matrix, but also emphasizes the importance of force chains, which are shown in part A of this figure. These are pseudostructures that occur when clasps are aligned within a rock and prevent interconnected pathways occurring within the matrix. This inhibits simple shearing within the matrix and means that the dominant tool that the rock will use to deal with deformation is brittle clast fracturing, which occurs at near lithostatic pore fluid pressures. These force chains are inhibited when these clasps begin to fracture, and the stress is redistributed to the matrix, which subsequently causes a sharp increase in strain rate, the development of a shear zone. These high strain rates of viscous deformation in the matrix can lead to transient slip events, and their duration is governed by local variations in effective stress and potential healing of fractures, both of which are ultimately controlled by pore fluid pressures. Overall, fluids are thought to be a key factor in the occurrence of slow slip at Cascadia subduction zone, due primarily to the fact that the elevated pore fluid pressures highly reduce the effective normal stress acting on ETS zones and allow the initial slip to propagate. However, their impact is not limited to this. There is also great evidence through modeling that fluids can impact ETS through their role in dehydration and brittlement, transient strain localization, microfracturing, and they can even aid with the regulation of the cycle through enabling silica healing of fractures to allow pore fluid pressures to rise again. There is still uncertainty in the details of this most peculiar structural phenomena, and whether fluids are the primary control of them is yet to be seen. However, it is widely accepted that they play at least some kind of role. Thank you very much for listening, and here are my references.